some of the characteristics and features that they have. Especially, we're going to be talking a lot about asymptotes. There are two types of asymptotes that we're going to deal with a bunch, and then there's a third type that we're not going to deal with much, if at all, but I at least want to kind of show it to you, and that it exists. So if you see it down the road later in AP Calc or in college or wherever you're headed next, that way at least you kind of seen it a little bit. Okay? I don't even know the title of the section. It's 3-7 is what it is. Alright. A popular misconception is that a graph may not, it should have the word not in there, may not cross an asymptote. That's a common misconception, meaning that a graph can touch or cross an asymptote. Now, does it happen often? No. It can never touch or cross a vertical asymptote ever, because vertical asymptotes are what would make our graphs undefined or have a 0 in the denominator. So it will never touch or cross a vertical asymptote. It can, however, touch or cross a horizontal asymptote. Again, does that happen often? No. But can it? Yes. So typically the way I think of asymptotes is I think about them like invisible dog fences. And I think about my aunt and uncle who live on the other side of the state, and they live out in the country. They have a huge yard, right? There's lots of acreage and just, you know, lots of outdoor land, and they have an invisible fence for their labs. And whenever somebody walks by, what happens? Right? They like run up to the fence and they bark, and they get all excited. They're like, come pet me, come pet me. They're not mean dogs, they just want to be pet. But they run really close to the fence. Do they ever touch or cross it? No. Maybe once in a great, great while they would. Maybe that fits my analogy too, right? But that's what I think of for an asymptote, is that it gets really, really close, but most of the time it's never going to touch or cross. Okay? So that's what we want to think about when we think about asymptotes. Another thing you can think about in terms of asymptotes is kind of how they behave or how the graph behaves along them. Oftentimes when you have an asymptote, your graph does what I call it hugs the asymptote. You see how it gets real close? Okay, so that's something that happens often as well. Alright, vertical asymptotes. Vertical asymptotes are in the form, x equals, third time's a charm. X equals a, and we are going to say that they are when, not we're going to say, they are when the denominator is 0, which would make it undefined, which is why our graph can never touch or cross a vertical asymptote ever. This is a spot where I am picky. So there are times I told you, times I'm picky, times I'm not. If you write an asymptote and I say, what's the vertical asymptote? And you say 2, I'm not going to give you full credit. You would need to write it in the form x equals 2. So remember, vertical asymptotes are equations of a line, so you need to write it as an equation with an x equals. Horizontal asymptotes are a little bit different. There are 3 situations that can happen, and depending on which situation you live in, tells you what type of horizontal asymptote you're going to have. So one option is that the degree of the numerator is smaller than the degree of the denominator. So the degree of your numerator could be smaller than the degree of the denominator. Let's see what that would look like real quick. So you don't have to just like picture it in your head. Let's actually look at an example. So f of x equals, we could have something like x plus 3 over x squared plus 2. Do you agree that my degree of my numerator is smaller? Because it's a 1 and my denominator is a 2, so it's bigger? Yes? Okay. So that's an example of what one could look like. If a situation like that arises where the degree is smaller in the numerator, you have your asymptote at 0. And just like with the vertical asymptotes, I would please also like you to write your horizontal asymptotes as y equals. Again, if you don't, I'm going to mark partial credit off because, again, x equals and y equals are not the same thing, right? One gives us a vertical line, one gives us a horizontal line. So vertical asymptotes need to be x equals, horizontal needs to be y equals. If the degree of the numerator is the same as the degree of the denominator, then the horizontal asymptote is the fraction formed by the leading coefficients. Let me show you what I mean. So, let's start with a function that would fit that. So let's say we've got g of x equals 3x squared plus 5x minus 10 over, can you guys read that still? Is it too small? It's okay? Alright, so g of x equals 3x squared plus 5x minus 10 over 5x squared minus 8x plus 9. Are my degrees the same? They're both 2, right? So my degrees are the same. So my horizontal asymptote is the ratio of the leading coefficient. So I would write y equals, because it's horizontal, my leading coefficients are 3 over 5. So if I looked at my calculator, I should have a horizontal asymptote at 3/5. And then we've got our last situation. So we're accounting for everything that can happen here. What if the degree of the numerator is larger than the degree of the denominator? If that's the case, then there is no horizontal asymptote. So what would that look like? H of x equals x cubed plus x plus 7 over x minus 4. We're just making stuff up. Again, you could have infinitely many different functions. I'm just giving examples of what one could look like. You see how my degree of my numerator is bigger? So that tells me that there's no horizontal asymptote. So those are the rules that you need to know and follow, and that's how you figure out what you've got. Okay, ready for some examples? Yes, we are excited for the examples. Alright, let's go with asymptotes. So it says find all the asymptotes. Think back. Do you remember when we were talking about problems where we had like a parabola and it looked like this? And I said find the min and the max. It had a max, but if this is my parabola, does it have a min? No. So not everything is going to have vertical and horizontal asymptotes. So just be advised that you might come across problems that don't have one or the other, and that's okay. That's something that can happen. Alright, vertical asymptotes, let's start there first. Vertical asymptotes are when the denominator equals 0. Okay, so I've got something quadratic. So you can try to factor it if you'd like. It is factorable. You can use the quadratic formula, or somebody last hour said, can I just use my calculator and find them that way? Yes, you can. Right? You go in there and find the zeros that way. Let's go ahead and let's try to factor though. Let's be brave. So we're looking for the vertical asymptotes. By the way, I abbreviate vertical asymptote VA and horizontal asymptote HA. Feel free to do the same unless you really want to write it out. Okay, 2 sets of parentheses, and we want to know when it equals 0. I'll tell you that it needs to be 3x and 3x. That's a huge hint. Put everything else in. You can find the rest. What should it be? -2 and -1. And it doesn't even matter which is which. So this is what we've got. -2 and -1. And that should multiply back out to what we needed it to. So we are saying that either 3x minus 2 equals 0 or 3x minus 1 equals 0 because of our zero product property. If I solve the one on the left, I would add over the 2 and divide by 3. So x equals 2/3. Add over the 1, divide by 3, x equals 1/3. So my vertical asymptotes are x equals 2/3 and 1/3. So you can write it with a comma in between, or you could write it out as 2 separate statements. X equals 2/3, x equals 1/3. Horizontal asymptotes. Which of the three situations do I have? Same degree. So what do I do? Ratio of the leading coefficients. So 1/9. And I have to write y equals or I'm going to lose some partial credit. Could I get on my graphing calculator and check that there are truly vertical asymptotes at those two locations? That there are error messages there? And could I check and see that most likely this isn't going to touch or cross 1/9? Right, so there are ways that you could check your work and look at the graph and make sure the graph matches up to what you think is going to happen. Alright, flip when you're ready. Are we good? Anybody still writing? Last page of the notes packet. Yay! Momentous equation. Almost said equation. The momentous equation. Oh, math. Alright, here we go. Part B. We want to find horizontal and vertical asymptotes. Vertical asymptote, this one's way easier. What is it? It's 1. That's not exciting. And we have to write x equals, right? The degree of my numerator is bigger than the degree of my denominator. So what do I say about that for horizontal asymptote? None. None, no. Part C. Vertical asymptotes. I'm going to factor and solve. This one's easier than part A as well. We want to find when it's equal to 0 because that's what we can't have. That's where our asymptotes live. So we know x times x is x squared. What multiplies to -4 but adds or subtracts to +3? +4, -1. 4 minus 1 is 3. 4 times -1 is -4. What would make this parenthesis 0? -4. This one? 1. So my vertical asymptotes are at x equals -4 and 1. Horizontal asymptote, the degree of my denominator is bigger. What do you have to say about that? Y equals 0. Okay, so we kind of ended up with one of each type. Alright, before we move to the next question, I want to show you something really quick. There is a third mysterious type of asymptote out there in the world that you could encounter, and I want to just make sure I show you what it is. We're not going to use it in this class, but I want to make sure that you know that it exists. Oh, hold on. 87, not 78, right? 87. Here we go. So here is the third type of asymptote that exists that you could definitely see next year in calc, wherever you are taking that class, if you're taking it. It's called a slant asymptote. What is it? It's an asymptote on a slant. Remember, mathematicians, we aren't very creative people. We tend to call things what they are. Like, slant asymptote is an asymptote with a slant. How do you know if you have a slant asymptote? If the degree of your numerator is only bigger by 1. Do you see how this is only bigger by 1? That's when I have a slant asymptote. So if that happens, the way you then calculate your slant asymptote is with division. You take your denominator and divide it into the numerator, and what you get as a result will be the equation of the slant asymptote. Okay? So that's how you find it. That's what it is. We're not going to do anything with that right now, but you may in the future.
Are you able to use synthetic division or just one?
You can use synthetic division. That'd be fine. Yep. Good question. Okay, so that is slant asymptote. Alright, moving onward. We want to make sure that when we're graphing, we graph all the important characteristics of our graph. So that means we want to make sure that we graph any asymptotes, horizontal or vertical. We want to graph any intercepts. We want to graph basically just everything that's a key characteristic of the graph. And we did just one last hour and people felt pretty okay with it, and so we're going to just do one this hour as well. Here we go. So first of all, let's find our vertical and horizontal asymptotes. Vertical asymptotes. Let's factor and solve. Bless you. X times times x is x squared. What do I need to multiply to get negative 6 to add to negative 5? Negative 3. Oh, I want to love it, but no. Still no.
Oh, negative 6 positive.
Look what I did to you guys. I was super tricky. Negative 6 and positive 1. Negative 6 times 1 is negative 6. Negative 6 plus 1 is negative 5. So my vertical asymptotes are x equals what? Asymptotes are funny. Back table. Okay. Horizontal asymptote. Is there one, and if so, where is it? 0. Okay. I'm going to draw in my asymptotes. Remember, we tend to draw in asymptotes as a dotted line. So I've got an asymptote at 0. And then I've got one at negative 1. I'm not going to graph my whole graph in pen because I'm not that bold, but I am going to graph my asymptotes in pen. Okay. Here we go. I'm going to use my calculator. You could always plug in values if you'd like to. I'm going to go to my y equals. I'm going to clear it out. And I'm going to press 6 divided by. And notice that everything is grouped in the denominator together, so I do need a parenthesis to keep all those things together. So x squared minus 5x minus 6. Close it, graph it. Ooh, cool one, right? Yeah, very exciting. Okay, are the asymptotes where we expected them to be? Yes? Okay, let's go ahead and find some points that we can graph. So if I go here, I can see that I've got a point at negative 2, comma 0.75. And if I keep going this way, do you see how it's getting closer and closer to 0? But it's never going to actually touch or cross. So this is one that doesn't touch or cross. And then it's going to take a turn upwards, and it's going to hug the vertical asymptote. So that's what that part of the graph is going to look like. Yeah, I guess so. Okay, let's find the middle section. So the middle section has something that looks like this. So I'm at 0, negative 1, and then I come up to 0.5 for 2 and 3, which must mean my max is in between them. And then I go back to negative 1 at 5. I'm going to draw on my graph. And then I'm going to go to the other chunk of my graph. So I've got one at 0.75 again. And it's going to do the exact same thing as the other side, where it's going to hug both asymptotes. Alright, let's talk domain and range. It looks like I wrote it in set notation today. So x such that x can be anywhere on this graph except for 2 locations. Which ones are off limits in terms of x? 6 and negative 1. So x such that x cannot equal negative 1 or 6. So what that tells me is my domain is anything else other than those 2 numbers. Sometimes it's easier to say what it's not than what it is. Because if I start listing out what it is, there are infinitely many things that it is, right? But there are only 2 things that it's not. So this is way faster and easier. Range. What's off limits for my range? 0. So we're going to get super duper close to 0. So we've got y such that we've got y has to stay greater than 0. and. Now, did this get up as close as it possibly could to 0? Do we know? We don't know. So let's go ahead and hit second trace, and we're going to find the maximum to see how high it went, how close it actually got. So left bound, I'm to the left of the max. Right bound, I'm going to arrow over and to the right of the max. And then for guess, I'm going to arrow kind of close. And it tells me that negative 0.49 is as high up as it gets. So y is also smaller than negative 0.49. I'm sure your book is writing the answers like this, otherwise I wouldn't have switched back to set notation from interval notation. So this is where we are for that. So that's how you're going to do those. It'd be similar for part B. So you look for your asymptotes, you graph it, and then you think about what your domain and range are going to be. One other quick thing that I want to talk about are holes in a graph. You can be going along your merry way, and then all of a sudden there can be a hole in your graph. So let's say you have a function that looks like this. What does my denominator factor into? X plus and minus 3, because it's a difference of squares. Do you see that this parenthesis and this parenthesis are a match? Like I have one that's the same in both top and bottom. If you ever have that happen, where you have the same thing in top and bottom, you're going to encounter a hole on your graph. I have a hole at, and it's what would make it 0. So I have a hole at negative 3. Now, here's the tricky thing about holes, is that they're not going to show up on your calculator. Your calculator is not a high-def TV, right? Like, we've got these, like, crazy awesome TVs, and they, like, curve now, and they're, like, 4D, and all the things, and, like, that's not what this is, right? That's not what this is. So, if I were to graph that, I just want to make sure you know, let me clear that out, I'd have parentheses, x plus 3, divided by parentheses, x squared minus 9. So if I graph, I'm still going to see that I have an asymptote at positive 3, but I also have a hole in my graph at negative 3. Can you tell there's a hole at negative 3? Does it look like there's a hole at negative 3? No. Again, it's not a high-def TV. You're not going to be able to see it. But if I go to my table and I go to negative 3, there's going to be an error message there. So that means there's a hole there. So on my graph, kind of like when we were graphing piecewise functions, I would have an open circle where that point is, and everything else would be connected. Okay, so just a heads up on that. Again, we're not going to encounter those much, if at all, but I at least wanted to mention those because those are something else kind of interesting that can happen with your graphs. Okay, you can grab graph paper from the back if that's something that would help you do your homework. We've got lots of time, so let's make sure we grab books and start working on homework. We are on assignment number 7. We are page 289 to 290, and we are going to do numbers 21 to 24, 31, 41, and 49 to 50. If it's obnoxious that I wrote this in the spot where the graph is, remember that you can look at the backboard too, and it's also written back there. I regret that decision. Okay, on your mark, get that though, you can work on homework.